Thank you very much, James. Great as usual. I actually want to relate to one point that you just talked about here at the end. And you said, that the infrastructure for carrying out analytics matters. So that's pretty much what I'm going to talk about. Our joint solution here with DDN is a database and the storage system that goes along with it. And I think that's really, really important. And the reason that's important is what we're seeing right now is that big data tends to mean sample data. This is an unfortunate side effect of picking maybe unsuitable infrastructure or not adapting the infrastructure as the data grows. We're seeing, of course, data is exponentially growing all the time. You have, every presentation you'll ever go to will say data is exponentially growing. We're collecting this amount of data and that amount of data. But the problem is it's really hard to analyze lots of data. So what you end up with is these systems where we kind of subsample, where we pick smaller amounts of data that may or may not actually represent the entire system very well. Now, you said also that many companies rely on analytics, and it's like 57% of what they do is analytics and BI, and these are strategic decisions that they're taking, but they may not be taking the right decisions if they're only looking at a small sample of data, which hasn't been very, very carefully selected. So there's an article that I saw a few days ago that I thought would be relevant here before we dive in. So the first problem we see is usually what the infrastructure tends to look like with an MPP database. So MPP is like multiple parallel processing, a massively parallel processing kind of database. It was first pioneered by Teradata in the 80s, but we're still, we still have many MPP databases around, things like Oracle Exadata and Netezza and Greenplum. These are all MPP databases. The problem with them is they have severe limitations. They're essentially databases designed in the 80s or still relying on, technology that hasn't really changed all that much. And because they're kind of transactional databases that have been repurposed, in order to power analytics and make the queries run fast enough, you have to take all these shortcuts and optimizations. Now, they're called optimizations, but in reality, they're really, really limiting. So you look at this kind of process where you have the data source coming in. Sometimes it has to be correlated, cleansed, or converted outside of the database. And then once it's in the database, you still have to do things like compression and partitioning. But the data is still not ready to be queried at this point. You still have to do pre-computations, create aggregated tables, materialize views, projections, cubing, indexing. There's a whole lot of different things that many companies do and many individuals do in these companies in order to get the analytics running. Now, the problem with that is you end up with these shallow reports. So every report that you planned on will run, and it will probably run pretty fast. But if one day you decide, okay, I want to add another dimension to this, I want to see how this relates to something else, if that wasn't planned, really, really well from the start, doing this now is going to take a lot of time. You're going to have to get, in large enterprise companies we've seen, you have to get signatures from like 50 people, and it's a month-long process at the very least. And by the time you actually get the data up and running, it may not be relevant. So it's kind of limiting your drill down capabilities and your reporting capabilities, and really limits the dimensionality. And this is not specifically true for only for MPPs. This is also true for the Hadoop world. So, and this is the problem. The average time that a company spends on data preparation is said to be about 60%, or more than 60%, according to the Gartner Market Guide for Data Preparation, which was published about 2 years ago. So this is a real problem, and it's not just, you don't have to take my word for it, and I'm sure a lot of you already know this, but Gartner says so as well, and I respect their opinion. The result of all of this is not just the wasted time, it's the wasted data, essentially. I said that, you have to sample the data, you have to select what's really, really, really important for your business. You only analyze about 10% of what you have. And we think that's not enough. We think there should be a bigger sample of data selected. You don't have to get to 100%. It's probably not going to make that much of a difference if you do 70% or 100%. But if you're only doing 10% or even less as your data keeps growing and your infrastructure doesn't adapt, then you're going to be left in an uncompetitive standpoint. And data is the key differentiator between different types of companies. And we see this a lot, for example, in telecoms. And I'll talk about that a little bit later. I have a case study for that. So I want to talk very, very briefly about our product. It's called SQreamDB, and it's a GPU-accelerated data warehouse. So essentially, it's a data warehouse. It's like Teradata, like Oracle, like Netezza. It's a database. You use it like you would with any other database. The key differentiator for SQream is the ability to look at a lot of data very, very fast. And we do that by bringing in a GPU into the mix. But it's not just the GPU. There's a whole bunch of different technologies, mostly software, that go into our product that makes it really adaptive, really well suited for big data analytics, and what we call high throughput compute. So when you're running a report and you're only looking at one day, that's not necessarily high throughput. But if you want to look at trends over 10 years, you really need that high throughput in order to look at that data and analyze the trends from that well. So our product is a GPU-accelerated data warehouse. It's powered by GPUs, but from the user perspective, it's an SQL database. So there's nothing really bizarre about using it to the user. They don't even have to know that it's, that there's a GPU in the mix. It integrates with pretty much every environment. So we can interface with Hadoop, we can interface with files on HDFS or other databases, either directly or through any of the ETL tools. Early on we decided to stick to standards. So we are SQL. We're ANSI SQL 92 compatible. We have ODBC, JDBC, Spark, TensorFlow, R. Everything is pretty much integrated right out of the box, so you can just drop it in and kind of start using it. The only kind of bizarre thing is that we have to have an NVIDIA GPU in the mix. So when we started creating the database a few years ago, this wasn't that common to get hardware with NVIDIA GPUs inside. But today we're really happy that NVIDIA is working with most of the hardware vendors around the world, and you can get a GPU-enabled server from any hardware vendor that you work with, plus on the cloud, which is fantastic. So I just want to tell you where we're sitting with our database, because it's important to understand that not every database is suitable for every use case. There's definitely a place for in-memory databases and NoSQL key value and regular RDBMSs for your operational data warehouse. There's still absolutely a place for those. We're kind of focused on the other end of the spectrum here, where we're looking at primarily analytics use cases on a lot of data, where we're not necessarily looking at one individual data item, but we're looking at the entire collection of data, where we're trying to identify trends, or trying to do maybe fraud analysis, or all these different BI reports that are very, very complex. And we focus very heavily on enabling ad hoc analytics. So the exploratory type of analytics, which would typically take hours or days on a traditional data warehouse, or even with Hadoop. And we try to bring that down to minutes and sometimes seconds. So we typically don't work in the milliseconds to seconds range. We work in the seconds to minutes and sometimes hours, depending on the query. That's kind of the world we live in. So, sorry, I jumped a few slides there. James mentioned earlier that GPUs have thousands of cores. That's absolutely true, and the cores are a huge part of this. But they're not the only thing at play here. We actually use the GPU primarily for its really, really high memory bandwidth. With a CPU, you typically get about 170 gigabytes per second memory bandwidth between the CPU and RAM. But with a GPU, we can get about 900 gigabytes a second. That's almost 1 terabyte a second of memory bandwidth. So that plays really well when we're doing something like a join operation. So we do all of our joins on the GPU, and a Tesla V100 can do operations at 900 gigabytes a second, about 33 teraflops of floating point operations. So it's an incredibly capable piece of hardware. But we absolutely do need the CPU in the mix and RAM. This all plays really well together. But it only plays well together if we have a storage that can actually feed this beast. And it is absolutely a beast. It's got immense bandwidth and immense capabilities, but we have to feed that. So the first thing that we do actually is we put the GPU to work for data loading. With a typical database, with a typical DBMS, what you see is you have your raw data, and that let's say that's 100 terabytes, and you write that to disk, and it may compress a little bit, and it may change some of the data format, and you'll end up with about 80 terabytes. But at that point, the data is not ready to be queried. This is what we talked about with the data prep. You still have to create materialized views or projections, or even something as basic as indexing, and that adds a lot of data, which is, primarily why a lot of companies say you shouldn't index on all columns. It's very, very expensive, and it's going to cost us a lot of disk space. We have to plan for this. So you end up with actually more data than you bargained for. You thought, I'm only putting in 100 terabytes, I'm going to compress it, but you still end up with more data than you bargained for. And only then is it ready to be queried. What SQreamDB does is a little bit different. We put the GPU to work for loading the data. So we actually use the GPU and the CPU for compressing every piece of the data as it comes in. And we end up writing, on average, about 1/5 of the data size that we would otherwise be writing. So we have GPU compression, we have CPU compression. We also have a very efficient columnar representation on disk, which means we end up writing about 1/5 of the data that we would originally write. On top of that, we add something we call this metadata, but in reality, this is like a BRIN index or like zone maps. So we collect some information about the data as it comes in. It's completely automatic and completely transparent to the user. All they know is they're loading in a file or loading in from a network, some network protocol, or reading a Parquet file. They don't have to care about all the stuff that goes on behind the scenes. But the second the data is ingested, it is ready to be queried immediately. There's no intermediate steps. You don't need to create indexes. You don't need to create these cubes or the materialized views. It's just there, ready to be queried. And we don't make you choose between, if you want to compress or if you want high performance. The compression is actually used to boost the performance, because the less amount of data that you read, the less I/O operations you have, and the faster the query will be. And this is really important because we're trying to save I/O, specifically for the network and for the bus all the way up to the GPU. Once we have the data compressed on the GPU, we can decompress it there. We have the massively parallel GPU, and we have the high memory bandwidth, and we can just decompress it. It's essentially a free operation for us. So we really like compression. We've done a lot of work on that, and we have, I think, one of the industry's only fully automatic adaptive compression, which actually changes compression types as it learns the data better. So that's pretty revolutionary. So I showed you at the beginning what you would do with a typical database. What you would end up with if you use SQreamDB, and we've seen this with many of our customers, is the architecture is massively simplified. So this can still fit in with the existing infrastructure. These data sources you see here, they can be another database, they can be files on HDFS, or on local storage, or on some network mount, or they can be another database, or this can be an ETL process. So some of these are direct loads, some of these are ETL process. You only need SQreamDB in the mix. Pretty much everything is automatic, and you can just run your queries directly off that, which once again connects really well with what James said, that the accessibility and the adaptability and the autonomousness of these new databases is important. And we've been doing this for a while now, and I think we have a really compelling product for this.